All right, so to finish off this discussion on all things chopping and mixing, I want to look a little bit into the message digest or MD family of hashing algorithms. You may know some of these beasts as MD2, MD4, and most notably MD5. And if you look up at the top of the screen, you can actually see the corresponding hash values for the input of Hello World for everything in this MD family. The site you're actually looking at right now is called CyberChef, and it's a pretty awesome tool to play around with some of these concepts in a pretty friendly environment, i.e. in a pretty non-technical way. So the idea here is that we get to be a chef where we're taking in some raw ingredients. So here my raw ingredients are going to be whatever message I want to shove into this. So I have hello world, but I could obviously change that up to whatever I want it to be. I'm then going to have a recipe that I need to live by. So that's where the chef aspect comes into play. I guess maybe that is lost a little bit because certain chefs maybe don't actually follow a recipe. They just throw some things together and hope for the best. But here we're going to properly follow this recipe. So my recipe here is to generate all hashes. And on the output, you can see this big old laundry list of a whole bunch of different hashing algorithms outputs. So hello world is then going to be converted into this just pile of garbage. I can also change these things up. So if I didn't want to generate all of them, maybe I just wanted to compute MD5. Maybe I wanted to take that output and then run it through SHA-2. So you can start to see this cute little stacking aspect in this recipe. You can also do some of the things that we saw in our bad hashing algorithm. So I can take hello world and I could convert it to hex. Easy enough. I could instead convert it to ASCII or Unicode. I'm going to drop this down. So when it's 16, it's obviously just hex again. But if I drop this to 10, it's then going to give me my traditional 72, 101, 108 that we saw then. I could also take those things and I can convert them to binary, which is how we actually played the game in our bad hashing algorithm. So I took hello world, I have the H, it got stored as a 72, or this beast in binary. And then in our bad hashing algorithm, we XORed that big old laundry list, and it kicked out something like a 32, or a 1 followed by 5 zeros. So you can play around with this thing for a very long time. It's weirdly entertaining just to stack all of these things together and just see the terror that emerges. We actually use this tool a bunch in our Gen Cyber camps for some middle school and high school students. As I alluded to earlier, it's a pretty friendly, non-technical way to poke around into this world a little bit. Basically, as long as you can type some things and click and drag, you can do some pretty chaotic things, which makes it pretty neat. It's also a good stage to kind of show the multitude of different hashing algorithms that do exist out there. So the top three that I mentioned, these MD2, 4, and 5, are these first three in this message digest family. And if you look at them, they're all going to have that nice fixed length that we alluded to before, and that we have to have a fixed length. So no matter what I'm going to put in this thing, you can always see that there's always going to be 16 bytes in MD5, 4, and 2. That's part of the design. It's also part of the problems with those things in that they're not super duper long. So we have 16 bytes or 128 bits. And if you go back to our discussion of the birthday paradox and some of these collision attacks, we at least mentioned that this 128 becomes kind of the bare minimum. Anything at or below this is going to start opening the door to having some potential collisions. So MD6, the most recent addition to the MD family, actually goes about doubling the length of the digest. So instead of having 16 bytes, it's now going to have 32 bytes, or what, 256 bits. So initially, this MD family was designed for cryptography, but there are some known vulnerabilities that have actually been discovered over time. So it's actually not recommended for that purpose anymore. It's still used to validate some file transfers, and unfortunately, it's still used in some cryptographic processes, but it really should not be. So MD5 still weirdly lurks around in a whole bunch of random things, so it should most certainly be swapped out for some of these other beautiful things that you see down on the bottom, namely things like SHA-2 and SHA-3. So SHA, if you've forgotten what it stands for Secure Hashing Algorithm. So you have a variety of different versions of SHA-2, as well as a couple different versions of SHA-3. So the number afterwards are going to then correspond to the length of that little digest. SHA-1 also exists up here. That one is basically in the same camp as MD5 in that there are some known vulnerabilities. So those ones should be thrown away in terms of the cryptographic procedures. And we should be working with some of the later, cooler things. So the guts of SHA-3 are super duper awesome. There's a whole bunch of chaotic mixing and twisting and remixing and chopping and mixing, and it's really neat. It is unfortunately pretty involved and a little bit beyond the scope of this course. So we're typically going to be living up here in this message digest family, even though those are not cryptographically secure. But they do give us a chance to kind of get our hands dirty and start to see what the underlying processes are, so you at least can appreciate what's going on in the SHA-3 world, so that later when you just hit import SHA-3 and then you just use that thing, you can at least be like, all right, there's a whole bunch of really cool mixing and chopping that's happening in the background, and I'm hoping that it's doing what it's supposed to do, because Mark showed me at least some early spinny crazinesses, so that SHA-3 I can appreciate what's actually happening in the background there without necessarily going full-fledged into the guts that are there. That's the little asterisk that I do want to allude to right now, is we're going to chat about some of the MD things. They're not cryptographically secure, but they do give us a fun little playground so we can start to see this terrible game of XORing and moving and shaking kind of in fashion, or kind of in the spirit of this world. So I do want to swap screens a little bit so I can at least present some of the big key components of some of these MD algorithms. And then I'll break it up into a couple individual videos of doing the checksum piece and then going ahead and actually doing the final compression piece. So if I want to swap my screen into my iPad and hope that things don't blow up on me, maybe find a pen. All right, so first off, we're actually going to have a really cool little picture. This is actually one of my favorite pictures. So in front of you should see three individuals back in the 1970s. They're probably in the wrong order, in that we have Ron Rivest in the middle, we have Shamir on the left, and then Adelman over on the right. So if they were presented with Ron over on the left, you would probably recognize these as the three individuals behind RSA. And one of these individuals, namely Ron, is also the brainchild of some of these earlier message digest things as well. So MD2 is back from 1989, and then he's been around in later developments as well. So he's both famous in that world as well as in this hashing algorithm, and just generally famous in most of these crypto systems as well. So the one that we're going to first start looking into is going to be the MD2 hashing algorithm, and there's going to be a variety of key steps. So we're going to do in this video steps 1 and 2 because they're the easiest ones. And then I'll do a separate video of computing the checksum, and then a separate video of actually doing our final little compression process. And then along the way, I'll pull up the code to actually show how we're going to go about doing those things. And then ultimately come back and check our answers with what CyberChef has, so that I can hopefully validate that the disaster that we're going to compute is also the same disaster that they had there. So there's going to be 5 big steps that are going to occur here. The first of which is we've actually done a couple times. It's basically take that phrase, hello world, and convert it into a list of these Unicode values. So the H going to 72, and so on and so forth. The next thing we want to do is we're going to pad this thing so that the length of that string has a specific structure. Basically, I want to begin working with blocks of 16. So ultimately, I would like my big old list to have length of a multiple of 16. So hello world only has 11 characters in it. So we're going to have to append a few extra things to it. So we're going to have to pad our message to actually increase the length so that the length is a multiple of 16. So that's what we're going to chat about in this video. And then in the next one, we'll actually do the following processes. Step 3 is then going to be to compute what's referred to as the checksum, which is going to look very similar to some of these parity bits that we saw in the error correcting code word. That's going to be appended onto the back end of it. So we're going to have 16 little things that we're going to jam onto the back so that the ultimate list is still a multiple of 16. And then we're going to begin the actual processing. So there's going to be a compression. So there's a mixing and a chopping and a mixing and a chopping. And then at the end of the day, that thing is going to be distilled down into a nice little list of 16 bytes. So we have that 128-bit structure. Cool. All right, so that's the game plan basically. So starting place, we're going to have hello world, which we saw before. In CyberChef land, we saw that we could easily convert this to a list of ASCII values, which we have here. We could also technically have it a list of individual characters, but that's really pretty boring. We could also convert it into its binary equivalents. Those are the ones that we then jammed through the XOR fashion. And we can also convert it into the hex world. We're going to be working up in this land because it's going to make my life a little bit easier. I don't have to draw out as many things. So our first goal then is going to be to do this padding. So initially this list has 11 things in it. So there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 11 things in this little list, and I have a really fat marker, so I'm gonna drop that down a little bit. So the thing that I wanna do is I wanna pad some things onto the back end of this thing to increase the length up to length 16. How we pad is going to be important in that we're going to want to know where our message essentially ends and where the pad begins. So you might be tempted to just add 5 zeros to the end, which would be totally fine, except for what would happen if my message ended in a 0. Then I would add 5 zeros, and I wouldn't know if there's supposed to be an end of 108 with then 6 zeros, or if that 0 is part of the actual pad. It becomes this kind of wishy-washy world. So instead of appending 5 zeros, what we're going to do is we're going to append 5 5s. So what that allows me to see is that if my message would have ended in a 5, let's say, if I pad on 5 extra 5s, well, I would see 6 5s, so that I would know that one of the 5s is part of the message, and one of the remaining 5s are then all part of the pad. And that's going to be true in general, is that the way that we pad this is always going to be to compute the needed length that gets me up to 16, and then I'm going to append that number that many times. So if I have 4 things that I need to add on to the end, I'm going to append 4 4s to the end. If I need to have 7 things to move up to a multiple of 16, I'm going to append 7 7s to the end. Do you see that? It's kind of this cute little way to identify where the message ends and where the pad is going to begin. The one kicker, though, is going to be what happens if your message was actually of length 16 to start. So if I had hello world and I tacked on, let's say, 5 exclamation points to the end of that, well, now this little block would then be of length 16. So then the question becomes, okay, now what do I do? How do I pad that? Or do I pad that? And the answer is we absolutely do want to pad. And the reason for that is, what would happen if my message would have ended with a singleton 1? The question then becomes, is that singleton 1 the end of the message, or is that singleton 1 a pad that took that 15 up to a 16? So if my message is genuinely of length 16 or a multiple of 16, what I'm going to do is I'm going to append 16 16s to the end of that. So I'm going to create a whole other block of 16 things that's going to very clearly say, all right, your message was of this multiple of 16, and then I'm going to pad on a whole bunch of 16s at the end. So it's a fun little game of padding. And that's actually the first 2 steps that we're going to have in this hashing algorithm. First, convert it to Unicode. That's pretty easy to do. Next, we're going to append a whole bunch of little R values. These R values are going to be how close am I to a multiple of 16, and then add those on over and over and over and over again until I get up to a multiple of 16. So if I need to add 5 5s, that's great. If I need to add 9 9s, that's great. If I have to add on 2 2s, easy enough as well. So those are the first 2 big components. Now we're going to chat about the checksum and then ultimately how we go about processing this, but I'm going to save that for some later videos. So I'm going to give this a pause as I change gears. So be back in a sec.